Hey guys, my name is Hiraku Murakami. I'm back with NovaEdge Academics, and today we'll be continuing with topic A5 Relativity, which is an HO only topic. Now, before I dive in, I just want to give a huge shout out to everyone who supported us through our journey. We've grown our channel considerably, and we are very grateful. And we also receive a lot of positive feedback through the comments and emails directly to us on how much of an impact we've had over your education in IB Physics. We also want to apologize really quickly that we haven't been able to upload as much for the past couple months. IB is finishing up for the second year 2 students, and year 1 students as well. They're finishing up their first year, and we received a lot of extra tutoring hours requests, and I've had to go and fulfill my responsibility as a tutor for those my students first. Given that, I couldn't upload as much, but we're back on track to give you a lot more content. So I hope this is useful in understanding relativity, and let's get right into it. So relativity is a very tough topic. Mind you, a lot of students who are even in university don't even know relativity. So it's definitely not an easy topic to tackle, but I hope that I can make this as simple and straightforward for you as possible. Now, the first thing to consider about relativity is that things are relative. That's the baseline of this topic, right? So relative to what is a question, and the relative to what is, well, it's relative to every person's point of view, and we call that a reference frame. So as an example here on this train track, right, we have a person here and on the train and a person on the platform watching that train go. From the woman's perspective, the train is moving to the right at, let's say, 10 meters per second, right? So if it's 10 meters per second going to the right, well, for the guy's perspective, right, the woman is actually going back at negative 10 meters per second. Mind you, it's negative because it's going backwards, right? So we can see that, things are relative to each other, and the question is, well, which one is a correct reference point to take into consideration? And the answer is that there is no correct reference point. That's the whole point of relativity, is there is no correct reference frame. And the reason why is because, well, even from woman's perspective on the platform, right, where we're technically on Earth, we are also still rotating. So Earth is rotating at 1670 kilometers per hour at the equator. So that means we, from an alien's perspective, we are also rotating at that significant speed. So, okay, so basically, who's the correct reference point? There isn't. We just take things relative to each other and we try to compute as is. And we've been doing that for Newton's physics, by the way. We've assumed objects at rest to be velocity equals 0, right? And when we say the ball travels at 10 meters per second, we're saying it travels at 10 meters per second relative to the ground, right? So we actually don't know what is the correct velocity of the object. We just know what is the velocity compared to something else, relative to something else, okay? Which gets into the core of Galilean relativity. Galilean relativity essentially just bridges different frame of references so that we can do math quite easily. And it's basically saying, okay, well, if the train is moving at this way and something else happens, what's the velocity of it relative to someone else, or relative to someone's point of view? Okay, and so essentially I want to break down, well, this is actually what's given in your data booklet, but I just want to break down this equation and how to use it, right? This is just rearranging from each other. I just want to show you how to use it, what the variables mean. Okay, so let me give you a quick example. So suppose the train is moving to the right. Of course, there's a woman on the platform. Now, suppose I roll the ball at 3 meters per second, and the train is going at 10 meters per second. Okay, so the train is moving at 10 meters per second, and then the man starts rolling the ball at 3 meters per second. From the woman's perspective, from the woman's point of view, right, the ball is going at 10 plus 3, 13 meters per second, right? But from the man's perspective, the ball is going at 3 meters per second, right? So there's a difference in what we consider to be the actual velocity of the ball relative to their own reference point. And that's essentially what this equation does. U here is from the woman's perspective, A. U prime is from the man's perspective, and V is just the velocity of the train, right? So when I put the equation, I can see that from the woman's perspective, the velocity of the ball is 3 plus 10, which is 13. That's literally what this Galilean relativity velocity equation, we call it Galilean transformation. Rearranging this, you get this. So they're basically isolating the the speed looking from the man's perspective is equal to 13 minus 10, which is 3 meters per second. Okay, that's basically it. So it's nothing complicated. When you say relativity, it's fancy, but it's just, addition of velocities to see what each reference point sees it as. Okay, and you're going to notice that all these equations, mathematical equations, is trying to bridge these two different reference points, or even more reference points, to try and bridge those and mathematically compute what the other person's perspective and how they interpret events to be happening. Okay, that's the core relativity. Now, if we can do it for velocity, we can also do it for position. So suppose there's a ball on the platform here. Okay, from the woman's perspective, again without the apostrophe, that's just x, right? From the woman's perspective, let's say that's just 10 meters. Okay, let's just say it's 10 meters, and well, the velocity of the train, let's say it's 5 meters per second. Right, so the man is traveling with the train at 5 meters per second. So you can see how, depending on the time, right, the man's gonna get closer and closer and closer to the ball. That's why we actually have velocity and time expression here. So, and the position of the ball from the man's perspective is x prime. So suppose, let me just use the second equation. Suppose I say, okay, what does the man see as a position of the ball after 1 second? So after 1 second, the man's gonna be traveling to here, right? Now he's in the middle. He's gone 5 meters from here. So the actual distance that the man sees from the ball is just 5 meters left, right? So it's actually just 5 meters, but we can compute that according to this equation. X prime is equal to 10, that's this one, minus by 5 times 1. 5 is a velocity, time is 1 second, and that's going to give us 5 meters, right? I can put different time, right? The more time I put it, the closer it gets to the ball. In fact, if it goes more than 2 seconds, it's going to go across, so it's going to see a negative value. It's going to be a negative displacement of, let's say, 5 meters, right? So this equation basically makes it easy for us to compute these type of things, okay? Now, one thing you're going to notice here is that there's one assumption we're making, which is these two have to align at t equals 0, right? At t equals 0, they're in the same position and time starts then. Train is already in motion. And the reason why I say this is because if the train starts to go at, some time delay, let's say it has a delay of 5 seconds, right? Then we're going to have to take into account into the equation. In fact, it's going to look like x prime plus v t minus 5. That's the time delay there. So this equation only holds when you can make the assumption that the train, that basically the reference point of A and B start at the same position at the same time. They are aligned with each other, okay? There's just one caveat you have to remember. So let's do a few problems to get a good grasp of what this Galilean relativity is. So pause the video and give this one a try. Okay, so a train's moving with a constant velocity. Ball is rolling 3 meters to the right. So train is moving at 16 meters per second, and the man rolls a ball 3 meters per second to the right. Calculate the velocity of the ball as recorded by an observer on the ground outside. I'm actually going to use the data booklet equation that they give you, which is this one. So u prime is equal to u minus v. Isolate u, I get u is equal to u prime plus v, which is 3 meters per second plus 16, which is 19. Okay, let's do b. Determine how your answer would change if the ball was rolling towards the back. Okay, so u again is now minus 3 plus 16, because the ball is now going towards the back. So it's 16 minus 3. And then last but not least, the train was moving the opposite direction. So train is going this way, 16 this way, with the ball moving this way. So it's going to be u is equal to 3 minus 16. Of course, unit is meters per second. Okay, so I hope that's clear. Let's do another one. Pause the video and give this one a try. Alright, so let's first calculate the distance between rocket A and the space station after 1 hour. So 1 hour is actually 1 hour is actually 3,600 seconds. I hope you know how to compute this. So using that, we can get that the x, which is distance seen from space station, right? Distance seen from space station is equal to 300 times 3,600, which is 1.08 times 10 to the power of 6 meters. Part B, according to observer in rocket B, so now I'm trying to get x prime. Okay, so what's x prime? I can actually use the equation. X prime is x minus vt, which is v is 200 and time is 3,600, which is 3.6 times 10 to the power. In rocket B's reference frame, determine how fast an observer would measure the rocket A's speed. Okay, so from B's perspective, which is traveling at 200, A is going to look like it's going at 100 because u prime is equal to u minus v, which is 300 minus 200, which is 100 meters per second. Okay, I hope that's as clear as it comes. Now here's the thing. We're going to get into the complicated part of relativity. I hope Galilean part was simple, but here's where it gets a bit complicated, and you're going to see in a second. So we've already confirmed using Michelson-Morley experiment that the speed of light is a constant at 3 times 10 to the power of 8 meters per second. And this is a universal constant. It's in your data booklet. You don't need to memorize, but I hope you do. And no matter what, the speed of light doesn't change. Like no object can be greater than this speed of light. Okay? But here is the problem. Here's a problem that we have. Okay? If I assume the train to be moving at the speed of light, right? So 3.00 times 10 to the power of 8 meters per second. Now if I roll the ball at 5 meters per second, what's the speed that the woman is going to interpret it as? It's going to be u is equal to u prime plus v, which is 5 plus 3.00 times 10 to the power of 8, which is greater than speed of light. And I mean, conceptually it makes sense, right? I mean, you're just adding the two. But in theory, this shouldn't be possible because nothing can be at greater speed than speed of light. And you might be saying, okay, well, the train going at this speed doesn't make sense. Okay, fair. So let me just flip it then. Let's say the train is moving at 5 meters per second, which is totally possible, right? And now let's say the man just turns on a flashlight. If the man turns a flashlight this way, then the light's going to be traveling at the speed of light, right? Okay, so same thing. What's the observer's speed of light, speed of this flashlight going to be? Well, it's going to be 5 plus this. That's not possible because we have to agree that speed of light from woman's perspective is also 3 times 10 to the power of 8, and the speed of light from man's perspective is also 3 times 10 to the power of 8. In fact, I told you earlier that the Earth is rotating, right? So if I have a person standing here and puts a flashlight here, right? Then that also has to be 3 times 10 to the power of 8 meters per second. But then also speed of sunlight reaching another planet is also 3 times 10 to the power of 8 meters per second. And these have to agree, even though I am moving at a very significant speed. So essentially speaking, this incoherency is what makes Galilean relativity not applicable for applications close to the speed of light, which leads us to the concept of special relativity. So there has to be some sort of a correction factor in order to compensate for this. And that correction factor is called the Lorentz factor. And so the Lorentz factor is a unitless factor, and it's always greater than or equal to 1. And it's given as this expression. Pause the video and give this one a try. Okay, so basically it. I hope you got the same answers. Now the key takeaway of this problem is that you should get something in the range of 1 to like 1.5. That's around where it's acceptable. So anything less than 1, you did something wrong. And anything that's like 3, 4, 5, it's really highly unlikely. It's going to be very, very close to the speed of light. So make sure you always double check and see if it makes sense. Now there's one more thing that I need to talk about, which is simultaneity. Okay. And this is going to lead to very important implication when we talk about Lorentz transformation. So pay attention to this one. So usually, you're watching this video right now. If I drop my Apple Pencil, we can agree on when I drop the Apple Pencil and when it hits the table. Like, that's pretty simple, right? And we can also agree if I drop two of them, that they happen at the same time, okay? And that's because we share the same reference point, right? We share the same reference point. We're stationary, both of us, and we're just watching the event happen. But what if we're not in the same reference frame, right? So going back to the train equation, right? Train example. I have a woman on the platform and I have a man on the train, okay? If lightning strikes at the back of the train and at the front of the train at the same time, or at the same time from the woman's perspective, okay? Well, from the woman's perspective, they struck at the same time, but guess what? From the man's perspective, let's assume the man's right in the middle of the train, right? From the man's perspective, who's traveling on the train at, let's say, v equals 5 meters per second, the front one is going to enter his eye before the back one enters into his eye. So he's going to register the lightning struck at the front of the train first, and then lightning at the back second. Okay, and obviously it's happening at the speed of light. So basically he's going to see almost that they're happening at the same time. But let's say I replace with sound. Sound travels a lot slower than light. So, lightning struck here at the same time according to the woman's perspective. But from the man, he's actually going to hear the first one first, then this one, because he is traveling towards the sound. So the sound is going to enter his ear canal first. So basically what I'm trying to get to is when we don't share the same reference point, okay, when we don't share the same reference point, especially when we're approaching the speed of light, then we're going to have this issue of simultaneity, okay, where we cannot agree on the position and the time of events anymore. Okay, this is a big issue, right? If I can't agree on the time and the place of events happening because we share different reference points, this is an issue, right? How do I correlate those two things? Well, we have to use something called Lorentz transform. And the Lorentz transformation equations basically allows us to see what the other person's perspective looks like. And that's why we use Lorentz transformation, which actually looks quite similar to Galilean transformation, but we also have time now, t prime. And you can see here, this thing takes into account simultaneity. So Vx over c squared is what takes into account this whole phenomenon where we cannot agree on time of the events happening anymore. Okay, so this is the Lorentz transform, which takes into account the special relativity aspect where you have the Lorentz factor and then the simultaneity. And so combining all of this, you get the Lorentz transformation equation. Okay, again, same thing as before. X prime is the position of events happening from the man's perspective on the train. T prime is also time of event from man's perspective on the train. Okay, so drill those in. Okay, X, position of events from woman's perspective. T, time of event from women's perspective. Okay, always make sure you know this. And V is always the velocity of the prime's reference frame. So basically velocity of the train in this case. Okay, so keep that in mind, and of course always keep in mind that Lorentz factor is calculated like that. And one more thing to note is, well, if I can find the x prime and t prime, I can also find the change in x prime and change in t prime, right? Change in displacement according to the other person's perspective. Change in time according to the other person's perspective. Okay, so this is just showing that you can compute these two as well. All right, so let's do a lot of practice problems. We're going to do 3 practice problems so that you can basically nail down the concept of Lorentz transformation and why it's useful. So pause the video and give this first problem a try. Okay, so Lorentz factor, let's find the Lorentz factor. Well, we actually already know because we computed this before. It's equal to 1.15. If you're not sure how, then check the previous slides. Part B, in reference frame S, events occur at x equals 5,000 and t equals 2. Calculate when and where the same event occurs as observed from another reference frame which has a relative velocity of 0.5. Okay, so we basically use these guys. X prime is equal to this. X is 5,000. V is 0.5 times c, which is 3.0 times 10 to the power of 8, and t is 2.0 seconds. Putting this in the calculator, you get negative 345 times 10 to the power of 6 meters. Okay? And C, state what assumptions you have made to answer part B. Again, when they ask about assumptions, you always say, well, we assume that the reference point S and S prime can agree on the time when the rocket starts moving. So they can agree at the beginning that T is the same. Okay? Let's try this problem. So pause the video and give this one a try. Alright, so the first thing you need to know is about light years. So light years is a measure of distance, and it's essentially speed of light times it by the year that it takes to get there. So essentially, if I say the distant galaxy is 30 light years away, I'm basically saying it takes 30 years with the speed of light to get there. Okay? So 30 years with speed of light to get to 30 light years. Okay, I mean, you're gonna see how I compute this mathematically. So let's do this one. So determine the coordinates. Again, same thing, right? So x prime is equal to Lorentz factor x minus vt. Again, same Lorentz factor because it's the same velocity at half the speed of light. X in this case is 20 light years minus vt. So vt has to match the unit of x. Vt has to also be in light years. So I'm going to keep it as c, and time here is 30 years. That's going to get me 15 light years here. So that's 5.75 light years. That's the coordinate from x prime, so reference point s prime perspective. Let's do t prime. T here is 30 years. So essentially same thing, right? This one has to agree with the unit, it has to be 30 years. And the Vx over c has to agree with the unit, it has to be light years. So V, I'm going to keep it as 0.50 c. And x is 20 light years. Remember, 20 light year is equal to c times 20 years. So c times 20 years. Okay, so 1.15 times by 30 years minus by 10 years. Okay, so that's 11.5 years. Okay, so x prime t prime coordinate is equal to 5.75 light years, 11.5 years. Okay, so essentially speaking, just to summarize, from reference frame S, the event, whatever it is, the event is occurring at 20 light years and 30 years. But from the other person's perspective, it's occurring at 5.75 light years position and at time 11.5 years. Okay? Let's try another problem to try and nail this down. So pause the video and give this one a try. Alright, same thing, but now the velocity's changed, so we need to recalculate the Lorentz factor. And you should get 1.51 or just 1.5. Okay, and yeah, let's calculate the x prime. Minus 200 meters. And t prime, same thing. You should get 1.64 times 10 to the power of negative 6 seconds. Okay, I hope you got the same thing. Again, just to summarize, from the perspective of reference frame S, the event is occurring at 250 meters and time equals this. From another person's perspective, it's happening at negative 200 meters and this seconds. Okay? We can also do Lorentz transform for velocity. If we can do, position and time, we can of course do change in position and change in time, and then we can also find the velocity, right? So recall from Galilean Relativity, we did the velocity correlation as this, but now it looks a bit similar to this, and it looks a bit similar to the Lorentz Factor, sorry. And that's because Lorentz Transformation takes into account both Lorentz Factor and effective simultaneity, right? So essentially, this is what you get, and you have to be able to use this equation. You don't need to know how it's derived, you just need to be able to use it appropriately. So let's try using it. Pause the video and give this one a try. Okay, so if we ignore the, Lorentz factor and simultaneity, the whole point of special relativity, and we just follow Galilean relativity, answer to this question is just going to be 0.20c, right? And when we use the Lorentz transformation, this is what we get. U prime is going to be u minus v over 1 minus uv over c squared. U is going to be 0.95c. .70c as the answer. Okay, so I hope you got the same answer. So it's vastly different, right? Before we would have taken 0.20c, now it's actually 0.70c after accounting for the whole special relativity, the Lorentz factor, and simultaneity. Okay. We're going to stop the video here on Lorentz transformation. Just to recap, Lorentz transformation was all about connecting two different reference points, taking into account the effect of special relativity. Galilean relativity did not. It just followed conventional Newtonian physics. But both relativity transformation equations are all about relating the same event, same event from two different perspectives. From my perspective, it might be happening at 5 meters at t equals 3 seconds. But from your perspective, someone who's traveling on a train, it might be happening at 3 meters at 1 second, for example, right? And the whole point of this math is to try and relate these two different reference points of the same event, because everything is relative from the perspective of each person. Okay, so that was the whole point of this lecture. Next presentation, we're going to talk about time dilation, length contraction, and the muon decay experiment. These are very complex topics as well. A lot of people have misconception of what time dilation is and what length contraction is. So I hope you check those videos out and stay tuned for those coming. Okay, so I'll see you in the next video. Hey guys, thanks for watching. If you like this kind of video, then consider giving us a like and subscribing to our channel. We have a lot more lecture style video and content like this in our channel, so feel free to go check it out. If you're looking for additional guidances like one-on-one tutors in IB subjects, SAT, TOK essay, IAs, writing, etc., then go to our website at NovaEdgeAcademics.com, fill out the form, and get in touch with us. In the meantime, we'll see you in the next video.